Hello everyone, welcome back. Over the next couple days, we're going to spend some time talking about a topic called optimization, which is the ability to find the single value that will either maximize or minimize a function. There are many different applications in business, in manufacturing, even in farming, where you are trying to use this concept of optimization. One of the most common is if you're trying to create a package for something and you want to maximize, for example, the volume given the materials, a certain limited quantity of materials. So there's lots of different places where different companies will use math like we are going to use in the next couple of days in order to answer these questions. Okay, I've listed out the steps here, and I want you to go ahead and get those written down. First thing you're going to do is draw a picture and make sure that you label the sides with the variables that you're going to use in the problem. Then there are two different equations that you need to identify. The first is the one that you are trying to maximize or minimize. This equation is called your primary equation. The second formula that you're going to write down is another equation that is given to you in the problem. So in the example that I was just talking about, you were wanting to maximize volume. Well, that would be your primary equation, but you were given a limited amount of supplies. So maybe your surface area would be your secondary equation. You're then going to go ahead and substitute the secondary equation into the primary equation, so there's only one variable. You're going to take the derivative, set equal to 0, because at this point now we're trying to maximize. So we are going to go ahead and take the derivative, set equal to 0, and prove that it's a max or a min using a sign chart. And then you're going to plug back in to find all the values that you asked for. Okay, so let's go ahead and get started on this first example. Find two positive numbers where the sum of the first and twice the second is 100. And the product is a maximum. Okay, so remember, if we look back to our steps, all right, the first thing that it told us was to find, to draw a picture if necessary. Clearly, I don't need to draw a picture here. But the next thing I'm going to do is determine my primary equation, which he said is the one you want to either maximize or minimize. So if you look for the word, okay, they want the product to be a maximum. So we have two positive numbers. So I'm just going to use the two numbers as x and y. Okay, so now we want their product to be a maximum. So I'm going to go ahead and say that my primary equation is x times y equals a product. Okay, I don't know what it is, but I'm just going to say equals p for product. All right, now I need a secondary equation. Okay, so my second equation is the one where I'm given a constraint of some sort. So if you notice, if you read through the problem, it said at the very beginning where the sum of the first and twice the second is 100. So if I take my two variables and translate that into an equation, I'm given a constraint of 100 where the sum of the first and twice the second is 100. Okay, so now I have two equations, a primary that I want to maximize, and then my secondary equation. Okay, the next step was to substitute the secondary equation into the primary so that you have only one variable. Well, it sounds like I need to get my secondary equation in terms of one of the variables. It doesn't matter which one, whichever is easier. So clearly, it's easier to get x by itself here by just subtracting 2y to both sides. Okay, now I'm going to go ahead and take that and substitute it into the primary equation. So I'll have, instead of x, I'm going to have 100 minus 2y times y is equal to p. Okay, I'm going to go ahead and distribute that. I have 100y minus 2y squared equals p. Okay, now I need to go ahead and maximize this, so that means I'm going to go ahead and take the derivative. So p prime would equal 100 minus 4y. All right, set that equal to 0 so I can find my critical values. Okay, so when I solve this, I would get 100 equals 4y, so y would be 25. Okay, so that should be the maximum. Okay, that should be the y value that will maximize this product. But we want to prove it using calculus. That means I need to set up my sign chart with p prime and p. Put your 25 on there, okay, which is a positive number. And if you notice, the original, it said they wanted you to find two positive numbers. So we're good to find 25. Okay, now I'm going to check a number smaller than 25, and remember I'm plugging it into p prime, so I'm plugging it into this right here. So if I plug in a 20, 100 minus 4 times 20 would be positive, so that means it would be increasing, p would be increasing there. All right, and then pick a number bigger than 25, so like 30, 100 minus 4 times 30 would be 120, and so that's obviously going to be negative, so I'd be decreasing there. That means my 25, this proves that the 25 will maximize the function at that point. Okay, at this point we need to go ahead and find our second number because the question asked for two numbers. So we found y is 25, that's our first answer. Now our x value would be 100 minus 2 times 25, so 100 minus 50 is 50. So our two numbers are going to be 50 and 25. Okay, the second example. A farmer plans to fence a rectangular pasture adjacent to a river. The pasture must contain 180,000 square meters in order to provide enough grass for the herd. What dimensions would require the least amount of fencing in order to reduce the farmer's expenses? Okay, so first thing we're going to do is go ahead and draw ourselves a picture. So we're talking about there is a river. Okay, and we want to go ahead and build a rectangular pasture adjacent to the river. So we're going to have something looking like that. Okay, now we're going to go ahead and look for our two different equations. All right, we need some variables in this, so we can go ahead and name those. So I'll just say that this is x and this is y. All right, so a farmer plans to fence that in, okay? The pasture must contain 180,000 square meters in order to provide enough grass for the herd. So if you read that, they're giving us, okay, a constraint. And so that must be our secondary equation. So we're going to continue reading to get our primary. What dimensions would require the least amount of fencing in order to reduce the farmer's expense? Okay, if I'm talking about fencing, if I'm fencing something in, that's talking about going around the outside, and that's perimeter, and the least amount, so I want to minimize my perimeter. So my primary equation here is about perimeter. All right, so if I were going around and adding up the outsides, I have an x here. Okay, I have a y, and obviously this is going to be another x. So I would say I would have 2x plus y is my perimeter. That's my primary equation. Okay, now I need my secondary equation. All right, so my secondary is the one with the constraint. The pasture must contain 180,000 square meters. Okay, square meters tells me we're talking about area. And so the area has to be 180,000 square meters. So area is length times width, so x times y equals that 180,000. Okay, now what we want to do is solve our secondary for one of the two variables so we can plug it into the primary. So I'm just going to go ahead and solve for y. It doesn't matter. You could do either one. Okay, and now we're going to take that y and plug it into our primary equation over here for perimeter. So 2x plus 180,000 over x. All right, I need to take the derivative of that, but in order to do that, I'm going to go ahead and rewrite this 180,000 over x as 180,000 x to the negative 1. Okay, so now I can go ahead and take the derivative, and I get 2 minus 180,000 x to the negative 2. Okay, so at this point I have to go ahead and set that equal to 0 and solve. So I would have, I'm going to rewrite it again with a positive exponent. Okay, so to solve this, okay, I'm going to go ahead and bring the 2 over. So I'd have negative 2 equals negative 180,000 over x squared. I would cross multiply here. So I get negative 2x squared equals negative 180,000. divide by negative 2, x squared equals 90,000. Take the square root of that. Well, let's see, there's 4 zeros, and the square root of 9 is 3, so that'd be 300. And actually, it's positive or negative 300, right? But since we are talking about perimeter, and we know that we have to always keep in mind the domain for these problems. If we're talking about the length of a fence, we definitely just care about the positive 300. We're going to reject out that negative. Okay, the next step is to create a sign chart to verify that this will in fact, remember we wanted to minimize the perimeter. Okay, so we wanted to have the least amount of fencing. I'm going to put 300 on here. This would be P prime and P. Oops. Okay, so if I test a number, and remember I'm testing it into P prime, so that was this one right here. Okay, so if I want to go ahead and test it and say 200, well, that would be 2 minus 180,000 divided by 200 squared would be 40,000. Okay, so this looks a little freaky, and especially to do without a calculator, but right now we can just get rid of all those zeros because there's 4 zeros top, 4 zeros bottom. And the question is 18/4 bigger or smaller than 2? And I would definitely say that 4 goes into 18 more than 2 times, so that means that this is going to be a bigger number than 2, so 2 minus would end up being a negative. And so that means it's going to be decreasing. The perimeter would be decreasing there. Okay, if I pick a number bigger than 300, say 400, then I would have 2 minus 18,000 divided by, okay, 400 squared would be 16,000, or I'm sorry, 160,000. So again, the zeros will cancel out. So now I have 18/16, which is definitely smaller than 2. So 2 minus, that would be a positive. And so I would end up with an increasing function at that place. So therefore, this proves that in fact, when x is 300, I will minimize my perimeter. Okay, so I now have an x value. If I go back and read the problem, it said what dimensions would require the least amount of fencing. So I need the full dimensions, all right? So I have the 300. I need to go ahead and grab the y value. So notice that my y is equal to 180,000 divided by 300. So that would be 2 zeros cross out. So I would get 600. Okay, so 600 and 300 would be the dimensions of that fence. Okay, we have 2 more examples that I'd like to get through. So number 3 says to consider the region enclosed by the x-axis and the curve f of x equals 9 minus x squared. Find the dimensions of the largest rectangle that could be inscribed in this region, assuming that its base lies on the x-axis. All right, so again, let's go ahead and draw myself a picture of what's going on here. So we're talking about graphing f of x equals 9 minus x squared. And so I know that it would cross at 9. I would have a downward facing parabola. Okay, and it's going to cross the x-axis at -3 and at 3. Now notice it says consider the region enclosed by the x-axis and that curve. So that means that I don't want anything below the x-axis. I'm just looking at this region, okay, right here. So from here and up here. All right, that's the region I'm enclosed within. Now, I am going to inscribe a rectangle into that region. All right, so if I inscribe a rectangle here, all right, you can see there's lots of different ways that I could do this. It says that the base has to be on the x-axis. So as long as my base is along the x-axis, I could have a rectangle like this. Okay, I could have a nice tall rectangle and thin. It could be really, really wide and very, very short. Okay, so there's lots of different ways that you could imagine. You could kind of have a more squared off rectangle. All right, so there is lots of different ways that you could inscribe a rectangle. So we're just going to go ahead and randomly choose one of these options, all right, that we think would look good. And we're going to inscribe it in. All right, now, if that's my rectangle, I need some variables to label. So this point right here I'm going to call XY. All right, that means I would have to move over x from the origin and up y. All right, so if I look at that, I can tell that the base of my rectangle down here would not just be x, but would in fact, there would be two x's, because I would be over x from the origin to the right and then over x from the origin to the left. And so this base actually is 2x, and it's by y, a height of y. Okay, now if we're talking about inscribing the largest rectangle, that's talking about area. So my primary equation here, okay, is that area has to be length times width. So here I have 2x times y. All right, now I need a secondary equation. So if I'm talking about my secondary equation, I have to be given some sort of constraint. Well, if I read through the problem, the only other constraint that I have is this curve right here. So in this case, you're actually given your secondary equation, and you don't have to do any solving or setting up or figuring out. You're just given it. So y equals 9 minus x squared. All right, so now you're going to go ahead and go back to that primary equation and replace the y value with 9 minus x squared. Okay, let's distribute that. I get 18x minus 2x to the third. Take the derivative of that, so I'd have 18 minus 6x squared. Set that equal to 0. Okay, I'm going to go ahead and move my 6x squared over. Divide by 6, so x squared would equal 3. So x would equal positive and negative radical 3. Once again, we are talking about dimensions of a rectangle, so I'm going to go ahead and throw out that negative, and I just have positive radical 3. Okay, once again, I need to go ahead and verify that really will produce a maximum. So I'm going to put root 3 on my curve. I'm going to label this with A prime and A. And I'm going to plug in a number smaller than radical 3, so I'll plug in a 1 into my A prime. So 18 minus 6 is definitely positive, increasing. I'll plug in a number bigger than radical 3, so say 3. So 18 minus 6 times 9 would definitely be a negative value, so decreasing. This proves that radical 3 will maximize my area, and so that gives me the x value. Okay, I go back over and find my y value. So y is equal to 9 minus radical 3 squared, which would be 9 minus 3, which is 6. Now be careful, because they want the dimensions of the rectangle. This x value here does not give you the dimensions of the length, because we needed 2 of those. So my dimensions would actually have to be 2 times radical 3, or 2 root 3, and then by 6 would be the dimensions. Okay, good job. Okay, number 4. This is one of my favorite type of problems. An open box with a rectangular base is to be constructed from a rectangular piece of cardboard 16 inches wide and 21 inches long by cutting equal squares from the corners and turning up the sides. Find the dimensions that will produce the box with the maximum volume. Okay, so I know that you've seen problems like this before. The idea is that we take this piece of cardboard here that they said was 16 inches wide and 21 inches long, and we're going to go ahead and cut these corners out, okay, that are squares, and then you're going to turn up the sides, and you're going to form a box that looks like this. It's an open top box. All right, so if we take a look at the only concept they're talking about here is volume, all right? And so we're going to take this piece here, and we're going to go ahead and figure out the length, the width, and the height for the volume of this box. Well, you can see here already that when you flip up this side, that the height of this box will be, in fact, x. Okay, but what about its length and its width? All right, so what happens if you look at the dotted lines on the base of the box, right? What are the lengths of those dotted lines? Well, if I start with the length, and I start with a length of 21 inches, and I take off, okay, I cut out this x and this x, well then what is left here in this dotted line is 21, take away 2 x's. Okay, and once again, for the width, if I start off with a width of 16, but I cut out x and x, then what's left for the dotted line and the bottom of the box would be 16 minus 2x. Okay, so think that through and make sure that you understand that. Okay, so those are going to be the dimensions for the bottom of my box, my length and my width. And my height, we said, was x. So the volume formula here is length, which was 21 minus 2x, times height, which was width, which is 16 minus 2x, times height, which is x. Okay, so if you look at that formula, we actually don't need, this is a unique case where we don't need a secondary equation because our volume formula is already in terms of only one variable. So I'm going to go ahead and distribute that all out. So I would have, let's see here, 21 times 16, big number, 336 minus 42x minus 32x plus 4x squared. And this is all times x. So my volume would be, I'm going to rewrite it, reorganize it, and get it all in the right way. So 4x cubed, let's see here, this would be minus 42 minus 32 would be minus 74x squared, and then plus 336x. Okay, I'm going to continue on and go ahead and find the derivative of that volume formula. So that would be 12x squared minus 74 times 2 would be 148x, and then plus 336. Okay, so that looks like a very ugly trinomial that I'm going to have to try and factor. So the first thing I can do, a 12 does not come out of all three of those, unfortunately, but a 4 does. So I can pull out a 4, and I'd be left with 3x squared minus 37x plus 84. And I admit I did a little bit of this figuring beforehand just to move us along here. All right, I would set this equal to 0, and I'm going to have to try to factor this. All right, so clearly I can see that this is going to be 3x and x. That one's obvious. All right, I can also tell because I have, it ends in a plus sign, and the middle sign is a minus, that I'm going to have two of the same, and they're both going to be minus. So now I'm just looking for my factors of 84. So let's see here. I know that I have 1 and 84 is a possibility, 2 and 42, 3 and 28, 4 and 21. So let's work with those. And if none of those work, then we'll keep thinking, okay? So 1 and 84, you can kind of tell, again, we're going to be adding these together. You can tell there's no way that I'm going to 3 times 84 or even 84 plus 3. No, not going to work. All right, 2 and 42. Well, if I had 42, I'm already over, and I'm going to be adding on to that, so that's not going to work. All right, next one, 3 and 28. Okay, so this one might be a little bit more promising. Obviously not 3 times 28, that's going to be over the 37 that I'm looking for. But what if I put 28 here and had 3 here? All right, that would be 28, negative 28, and then negative 9, which in fact does add up to negative 37. So there we go, that is the factored form. When I t-chart that, I get x is 3, and I get x is 28 thirds. Okay, so I have two different x values. So I definitely am going to have to do a sign chart in order to verify which of those will maximize the volume. Okay, so I went ahead and started out my sign chart here. I put 3 and 28 thirds on there, and I have V prime and V. So now I'm going to go through and I got to test different values. All right, so picking a number, and again, we're testing it into V prime, so probably easiest to test it all the way into the most factored form. So if I put in a 1, well, 3 times 1 would be 3 minus 28 is negative, 1 minus 3 is negative, so I'd have a negative times a negative, which would be a positive, which tells me it's going to be increasing there. All right, picking a number between 3 and 28 thirds, a 4 would work. 3 times 4 is 12, minus 28 would be negative. 4 minus 3, though, is positive, so that would be a negative there, which would mean it would be decreasing. Okay, 28 thirds, a number bigger than that, well, clearly 10 is bigger than that. So 3 times 10 is 30 minus 28 is positive. 10 minus 3 is also positive. So that would be a positive increasing function. Okay. All right. So now I have those. And so now I can say that for sure I am going up to reaching a maximum at 3 and then reaching a minimum. So this is my max and this is my min. So since I wanted to maximize the volume, it is the x equals 3 that will maximize the volume. All right, now we wanted the dimensions of the box. So x equals 3 would be your height. Okay, my width was 16 minus 2 times 3, or 16 minus 6, so 10. And my length of the box was 21 minus 2 times 3, or 21 minus 6, so 15. Okay, so those would be the final dimensions for that box, and we are all set. Good job. All right, so this is the end of the first video on optimization. Please make sure that you took good notes. We are finally going to be back together, and we will be going over this next class as well as a few other just kind of loose ends to make sure that we're all on the same page and ready to move forward. Thanks a lot, guys.